Uno, dos, tres. Окей. Окей.
Хорошо, спасибо.
Спасибо.
Так, вот спросите ваших. Все.
Кто там сейчас присутствует? Так, я, честно говоря, Даниил, скажите, вы слышите нас?
Да, вас слышно.
Все отлично, нас слышно, поэтому мы можем начинать. Спасибо.
Maybe in English this time. Maybe in Spanish.
Spanish is a good language.
Okay.
I'm afraid nobody speaks English.
Okay.
So let us stick to something like
Yeah, in English, I guess. Yeah, I'm not sure I can do it in Russian, but I can try.
yeah, I'm not sure you can try. But when I'm not sure, I usually prefer not to type it or something the same. So just to be on the safe side, let's speak English today, okay?
Okay. So
So
let's
today
start.
our speaker is Abner Rodriguez.
Hernandez.
I probably should do double name, right? Abner
Yeah.
Hernandez.
Yeah. Familia это Hernandez Rodriguez.
Okay, sorry. Hernandez. And he's going to speak about double Poisson structures on algebras and give examples of such structures in low-dimensional cases.
Okay. Well, as Shergen said, yeah. Okay. Let's start. First, an introduction of the classic way of how integrable systems are approached. So, in classic way, we used a smooth manifold, and we use something called Poisson bracket. So, the Poisson bracket has to be antisymmetric. You may all know what is it, but in general it means like AB is the same as BA. Of course, it is a map, linear map. Sorry, yeah, from the algebra of smooth functions, the manifold. To itself. It has to be antisymmetric, follow a Leibniz rule. It means it's a derivation in each entrance. For example, this, it means satisfied Leibniz rules, and the final, the Jacob identity. So for any elements in this algebra, ABC, it satisfies plus the cyclic combinations, it's just ABC. Equals to 0. So this is the classic way to approach integrable systems. But in a more general way, we can substitute this algebra by algebra, associative algebra, and let's assume it's commutative. And we can still talk about integrability with this language. Just we take these elements in these algebras. Yeah. But what happens when we do this? Well, if we take the case where when A is commutative, is abelian, then something happens. In particular, for semi-simple algebras, we get that all Poisson brackets are inner derivations, actually. That means that for AB, any elements in this algebra, it can be seen as just the commutator of a linear function evaluated in A, B, or also in the other way, also for B, we just plug in here a linear function. Well, okay, a linear map. And then, so if we use Jacob identity, it follows that actually this only linear. It is indeed just multiplication by a constant. Central element, okay. And if it's abelian, then we just get here 0. So it's not actually very interesting. But if we assume that our algebras are non-commutative, then to induce
Abelian algebra is not semi-simple. Abelian algebra is not
Actually, semi-simple Abelian algebras.
yeah, this example we just take out the abelian case.
The Abelian relative algebras cannot be semi-simple, I believe, except for some very trivial case like the ground truth case.
Okay.
But in any case, in the case of commutative algebras that are supposed to exist, they can exist different examples as well. But for instance, in the case of algebras, commutative algebras, the algebras of functions on manifolds, in this case you can also do this. But in most non-commutative cases, you can hardly find anything except for the commutator. In most commutative cases, they either, even if they're not semi-simple, they include something semi-simple, something like that. So it's really hard to find anything except for that.
Okay. So now that we take non-commutative, A, associative algebra, non-commutative over a field of characteristic 0. So following a philosophy by Kontsevich, if we want to get a notion of geometric meaning in our algebra or the ring, this ring A, it has to induce also the same notion of the geometric notion in the space of representations. It means if we want to get a Poisson bracket here, we can also get a Poisson bracket here, which we have to. And
It means that representations is models.
wait, okay, I'm gonna write what are these. Well, in general, just homomorphisms from the algebra to the, well, in this case is N, so to the algebra of matrices in the field K. Yep. So just functions. Okay. Such that. Okay, so now we can translate our notion of Poisson bracket in the algebra to Poisson bracket in representations of an algebra of size n. So, how does the day look? So we have a representation, an homomorphism, but also to define a Poisson bracket in this space, we need to define a Poisson bracket for the coordinate ring of this space. The coordinate ring of this space looks like next. So they are defined by some functions. Here.
And this you treat it just as vector space, yes? So this representation is just a vector space.
This, yeah.
It's just so it's not an algebra, just vector space.
Yeah, it's in a vector space, yeah. Sorry for that. Yeah. Okay. So we take the ring, well, the ring of the representations. And, okay. When we get a representation,
It's the space of all maps as an algebra, for algebra homomorphisms.
Okay, I understand. But I mean, for Poisson bracket, you need you always ask for the Leibniz rule.
Yes.
And for Leibniz rule, you need some multiplication. What
we're gonna use. I will.
Okay, we are speaking about functions on the representation space, and of course, when you have functions, you have multiplication.
Yes.
There's no problem.
Okay, so for our representation, we want to, because it maps the algebra to an algebra of matrices. So we take X and it maps to a matrix, but this matrix we can define it just the entrance of this matrix in this way, and these functions are the coordinate ring of this of the representation space, right? So what they do, you give them a representation and they give you just a function. So in general, they are functions here. So you give them a representation and they give you a number.
Yes.
Right? So in the entrance of, there's a matrix, because these representations have to map to a matrix. Let's say this matrix. Just to explain what is this guy. But to see it in a more general way, we can consider these as functions that depend on the representation that you gave to them. Right? So x, you just send them to the matrix according to the coordinate ring. Okay. Okay, maybe let me rewrite it to be more clear.
So this is a coordinates
Mm-hmm.
on representations of AL.
Yeah, but let me, okay, you have an element in the algebra. Let's say A. A is in the algebra. So you take a representation that takes this element to which matrix you want to know which matrix X is a representation.
Okay, yes.
Uh-huh. So X acts on A. Like you have to get a matrix. So what is this matrix? What we want to do is like generalize. How does it look? So we define the entrances of this
Just some
of this matrix just as a okay. No need to write that. Like these coordinates are this function evaluated here.
Okay, okay. Okay. This is in the dimensional space, yes.
N-dimensional, yeah.
M-dimensional.
Ah, the homomorphism there.
Yes,
Yeah.
dimensional.
No.
Oh,
Space of all homomorphisms is actually an algebraic variety, an affine variety. Let's say that you need to assume that A is finitely
Finite.
represented. Yeah, let's make this assumption. That's A is finitely presented. I mean, that is it is limited by finite number of generators, very finite number of relations.
Mhm.
Because infinite finite number of relations can be a bit tricky. So if you have a finite number of generators and finite number of relations of them, then you can actually associate to every homomorphism a finite set of matrices that is another point in n squared times the number of matrices dimensional space, finite space, where you find a finite number of algebraic equations.
okay.
So that gives you an algebraic, a fine variety of very large dimension in general, and pretty wild, to be sure, but still it isn't fine. It can be pretty singular, very singular in fact.
Is it finite as a vector space?
What?
The-
Space
the-
of functions is not finite.
Algebra.
No, it's not finite. It's not finite. It's finite dimensional. It's not even finite dimensional. It's just finitely represented algebra. That is to say, it has finite number of generators and finite number of relations.
Yeah, I don't know. It was clear how it's finite represented. It means like okay.
It's a free algebra factor by some
Uh-huh. Yeah,
free.
but also yeah, like A it's just generated by a finite like finite elements, and it has some finite relationships. That's all. Okay, so to induce a Poisson bracket here, we have to say what is the value in these ones. So if we just check, like, yeah, it depends on four indexes. So it gives us the idea that we need a structure like a map that acts on the tensor product of this algebra. And that is and that's how are introduced the double Poisson brackets.
As far as I can understand, this is in fact generators. It's not a whole algebra spanned.
Ah, no, it's just like the definition
I
of
mean,
finite
O,
representation.
when you write down O of A comma N, it is it's the algebra of polynomial functions.
Yes, and
And you define these polynomial functions in this way.
yes, I got it.
Mm-hmm. Okay.
Excuse me.
Yep.
Well, I joined a bit late. If we take the algebra, for instance, super, you know.
Did you take a super algebra?
Sorry, I don't hear you.
If I take here x1, except not from free algebra,
Yeah.
from Graphman algebra, for instance, would it work?
In general, it works for any algebra, this construction.
So what's the question?
It's not a free. If it's not a free
It's
algebra,
not free, then you have relations. And of course, the space of representations can be empty. It can be, it's possible. It's possible that there are no representations, unfortunately.
Yeah.
But we have very little control over the size of this space. Yeah. Is this clear?
Well, I didn't see examples on other algebras.
Ah, we're gonna show some
Yeah,
examples.
there will be examples today. Yeah, sure. Very simple examples, of course, but there will be.
Okay. So, where is double Poisson brackets? They are linear maps from a tensor product of an algebra itself. So yeah, just to clarify, A and then represented over a field of characteristic 0, and we're going to consider it non-commutative. So we're going to ask to this map to be a modified version of antisymmetricity. It will satisfy A, B is equals to minus BA. And we're going to use this notation here. What does it mean? It just means, because this is in the tensor product of the algebra. So let's say AB, when we just write a circle, it means we just transpose the elements. This. Now, it has to be derivation in the second entrance. But with the structure of outer model. So we take A, B, C, and we map it to, we multiply by B tensor 1, AC plus AB multiplying by this guy. This is our version of derivation here. And last, it's a modified Jacobi identity. It's a little bit longer, but I'll write it. Okay. First, we're gonna define it. Just there are some elements here that need to be defined. So. this is the usual double Poisson bracket, and here we're going to use an index of L. It means left side, but we want to mention what is this. And a transposition here, because this is already in the tensor product, triple tensor product of the algebra. So this transposition only means these elements, we transpose them according to this rule. Left n plus the last element is 1, 3, 2. So who are these guys of the L? So these guys of the L means after we apply, let's say A, and we have a tensor here, B, C, L. So this is equals to A, B, but the usual double Poisson bracket, multiplying just multiplying C. Yeah. This is already in the triple tensor product because this is in the double tensor product. And that's how we define a double Poisson bracket. Now, what we can do with it? Well, we have to be sure that actually if we get a double Poisson bracket, we can induce a usual Poisson bracket to the algebra.
We don't erase the algebra.
Okay. So how do we induce a Poisson bracket from a double Poisson bracket? There's one. Okay.
Multiply the answer.
Similar. There's multiplication implied, but it's a little bit tricky. J, B, L. This means the first component of the tensor product, and we multiply the second component of the tensor product, but I think this is IK. This is because I confuse with the indexes.
But here you don't need indices, no?
Yeah, because we're gonna act on the coordinate ring of the representation space. IPQ. Yep. So it's KJ. IL.
So this is the bracket on the O on the our on the home on the
This acts on the algebra, and these are in the coordinate ring of the representations. Okay, now some examples of such structures. Maybe here. Well, there's one introduced by Van Den Bergh in his article. Is if we consider the algebra as just polynomials in one variable with the field of characteristic 0, then the only two Poisson structures in this algebra, it's enough to define the double Poisson bracket in this basis, right? Because we can use just Leibniz rule and everything else. So and these are actually the only two Poisson structures here. Now, there's a second example of such structures. If we consider free algebra, this was an example provided by I think Sokolov and Rubtsov, and forgot one name. But they computed all some double Poisson structures in free algebras till second degree. Because here because it is free, we can just calculate more, considering more powers of the generators. So the one that I will introduce is just of linear order. So. Minus and zero, I, K, and 1x. And down is K. Yeah. There are some relations between these coefficients to satisfy the rules of sanity symmetricity, derivation, and Jacobi identity. They are kind of long, so.
I believe B, the new B, I should just define the structure constant on some associative algebra.
Sorry, again. Here?
B only should define the structure constants of some associative algebra.
It's not arbitrary.
Yeah, no. I mean, there are many relations. Only for Jacobi identity, there are many. So I don't want to
Actually,
really.
you can rewrite even this formula. As you see here, we assume that the right-hand side depends linearly on the generator's next side. Instead, you can assume that it depends
Quadratic
on
or
the
more.
side. But that's just the simplest example. And yeah, you can, if you check all the identities for B, I, J, K, you will be able to verify.
If you take, assume that you have free algebra, for simplicity, take C of x1, x2. So free algebra is C of x1, x2, and there is operator. This operator will be dx1 tensor dx2 minus dx2 tensor dx1. Will this operator define the structure of double bracket or not? Is it obvious or not? Because the first two properties are obviously satisfied.
For a free algebra?
Yes.
Well, yeah. I mean, like this is not enough. Like there are many other relations that they still have to satisfy. But yeah, they definitely will do. Like actually, what they have in common is like these algebras are of infinite dimension. And actually, it's a little bit easier to get examples of infinite dimension. What we try to do is get examples of finite dimension, because actually the computations to get to calculate them are not really easy. They get yeah.
All the examples which are known today, they are usually infinite dimensional. They are either free or something very simple which you obtain from free algebras. Well, most, I think the most interesting example which is known today, I believe, is the example of Poisson structure, double Poisson structures on the path algebras of
Quiver algebras?
Yeah, of quivers. Quiver algebras. In that case, you can actually use this combinatorial extraction of quivers to reproduce this double Poisson structure.
Yeah, something else I would like to say.
I mean, if you take di tensor di minus di tensor di.
What is DI?
Yeah.
You have this. You take for instance two-dimensional free algebra. The free algebra on two generators. And you take dx1 tensor dx2 minus dx2 tensor dx1.
What is D?
Yeah, I don't get it.
Differential.
Oh, it's free differential.
It's just differential. So the algebra of polynomials, and they can differentiate them.
Yeah, so you add this differential.
And you take dx1 tensor dx2 minus dx2 tensor dx1.
Okay.
Will this thing define the structure of double Poisson?
Oh, so which is just
With two generators, you need a little bit more.
it's a good question. First of all,
Because first two properties are
yeah, first of
always
all,
satisfied.
first of properties are verified, and in fact, it is the only non-trivial double structure which there can be, right? Oh, except for the fact that you can also define the commutators of double commutators of x and dx, x1 and dx2, something like that, unless you assume that d commutes with this double structure. Do you assume this or not?
We can discuss it after.
Yeah, I mean, of course, we need to define these commutators for all pairs of generators. So if you define it for x and y, that's okay, but you need also to define them for dx and dy if you assume that they're independent of x and y in some sense.
Yeah, let me show you an example with matrices to see how it is to computate them. Okay, just okay. This little bit long, so may I erase the definition or I keep it there? Okay. Okay, what would happen if we want to calculate some double Poisson brackets in an algebra of matrices? So let's consider the algebra, the whole
I'm going
algebra.
to speak about an example. The first example is the algebra of matrices. And
Yeah.
we want to prove that modulo certain evident examples, there are no other double Poisson structures. Yeah.
But first I want to just show how it's like the process of computing, like how it gets,
Involved.
yeah. So let's calculate this. So we have to, for this one, we can model any matrix here. Just some. It's a sum of some brackets. Yeah. No. Here.
Now, so
Yeah.
let me just make my one remark. So unlike the previous example where we work in free algebra, these EIJ, they're not just generators of the algebra, they're in fact bases. And therefore, we can just always assume that everything, both on the left and on the right, is expressed in terms of these elements.
Yeah.
That makes it.
So we have
easier,
to
not more complicated.
say who are these guys. Have to say where are they mapped. These are the generators too, so this can be represented also in languages of these generators, but already in the tensor product. So we have to determine what are these coefficients and how they are related. With all indexes, from 1 to n. So there are pretty large number of coefficients to be calculated. So just for antisymmetricity, we have to get that these coefficients actually this is we want to prove that this is we want to calculate what have to satisfy these coefficients if they satisfy antisymmetricity. So we get AKL and we pass to the other side IJ and we transpose them. So, yeah. So how it looks, we know how they look, just we move the indexes. So it's phi, alpha, beta, gamma, beta. We just rename them. Okay, L, IJ, E, alpha, beta, E, gamma, delta, and we do the change. Tensor product with the alpha beta. You see, because we just changed this from the side. That's what we did. So this has to be minus these coefficients. You just rename them to be more similar to the entrance. We just renamed this. C, D, A, B, K, L, I, J, and then we use the same basis as up, well, in the same order. Yeah, so what we did, we get that these coefficients have to be like these ones. These are the relation that they get just for antisymmetricity. This eliminates some coefficients, but not all. So not many. So we continue. For derivation in the second entrance, we get, well, we just rewrite. We know how looks the multiplication of this basis. Ij, A, L. It's just a delta function, k, and again in the basis. So after some commutation, just to, okay, what is this? It's just a sum to 2 of PQ equals to 1 of some deltas, delta JK, delta Pi, delta QL, delta, no, that's enough, yeah. Now EPQ, yeah, that's how we represent. Now we just substitute this by some coefficients that keep all the information. So let's call it C, CPQ. I, J, K, L. Applying EPQ.
Is the structure constants of algebra, right?
Yeah, of how it looks when we multiply. Yeah, these are the structures, the structure constants. So we just plug in this in the Leibniz rule. Well, in the derivation in the second entrance. Okay, maybe I will not make it that long. Just
Don't give the details.
yeah, just after some computations, we get to the final rule. That to get Leibniz rule, well, derivation in the second entrance, we need the coefficient to satisfy this rule. J beta gamma delta A B K L plus delta L phi alpha beta gamma kappa okay A B I J plus minus delta J K alpha beta gamma delta A B I L. This equals to 0. So we can just add also the previous rule for antisymmetricity, just phi A B C D I J K L equals to minus phi C D A B I L I J. And also just for Jacob identity, I'll write it right here, but it's following the same idea. We get phi alpha beta gamma delta and k L M N multiplying another phi W omega X Y Z I J alpha beta plus phi alpha beta omega X M N I J phi gamma delta K L alpha beta plus phi alpha beta Y Z J K L phi gamma delta W X M N alpha beta, and this has to be 0 for Jacob identity. So even just for n equal to 2, this is barely computationable, but if you already, like, I don't know, if you put this in a computer and you run it to solve it, just these equations, it will take it maybe an hour or more. And when you already plug n equal to 3, it just breaks. So
The number of elements here when n equals to 3 would be equal to 3 to the power 8. 3 to the power 8 is how many is it? I lost it. Yeah. I think it's 81 squared. And the number of equations is 5.
yeah, because when you have infinite dimension or just free algebra, your Leibniz rule becomes slightly more simpler, and you can eliminate more. And
Have you seen Ruptsov lectures on these topics? No?
not really.
They write this equation in some, Ruptsov and his colleague has a lecture called Lectures on Poisson algebras. And the last part of this lecture is dedicated to the double Poisson bracket, and they write this equation, the last equation, in some fashion as people with their matrices, right?
Oh.
So it's written like R1 2 times R something.
That's interesting. It's possible to have it as a matrix, right? It looks like R matrix. You're right.
But our matrix is to give this notion of
It's like, but not
of
classical.
of Leibniz.
Classical on one hand, but
It looks like the half of the classical
Yeah, half
Baxter
of-
equation.
It's precisely half.
It's
not-
precisely half
Yeah.
the classical Baxter. It's interesting. It's very interesting.
Yeah.
So,
So there's another approach to this, how we solve it.
at least in metrics, I was in case of metrics.
Yeah. Well, there are some results by Van Den Bergh that we prefer to use instead of just trying to solve these equations. So there is a map. It's in the article of Van Den Bergh, by Van Den Bergh. So
let me before Abner proceeds, let me mention that on one hand, the case of free algebras is simpler because you don't have the main problem with this is actually the first equation. Leibniz rule is actually the most important because as far as the second and the third equations are concerned, the second is just linear. It has nothing to do with algebra at all. Just linear equation. It's just symmetricity. It's very simple. And the third equation is it's again looks like matrix, and there are lots of ways, lots of methods of solving such equations. There are lots of examples. But the actual difficulty comes from the attempt to incorporate the Leibniz rule, because the Leibniz rule depends on the algebra. So we cannot just even though this first equation is linear, even though this Leibniz rule equation is linear, it depends in a very specific, very hard way on the structure constants of the algebra. And therefore, we cannot just omit it. We cannot just hope that we find a universal way of solving such equations. I don't think that there will ever be a universal way which will not depend on the structure constants.
yeah.
Okay.
Yeah, I tried to mention that. Yeah. Okay. So there's a map. It's actually a proposition. So how it's called? Okay, let's call it mu. And we map the derivations this is an algebra that depends on A. A is an algebra also. This is the algebra of derivations of A. D, B, A. This is just derivations B. This. And we map them to the set of B linear double brackets
What is B?
B is just a module. It's a subalgebra, or
Actually,
it's
you
a
can just
module
write
that
K.
acts on A.
You
No.
can just write K here.
Okay, yeah, that's right, just K.
K is base.
Yeah, it's basic.
Double brackets on A. Yeah. So, if okay, the proposition is this is well defined. And another proposition is that
Let's write down the formula for
the whole thing. Okay.
This proposition makes no sense unless you give the construction of mu.
Okay. Q. Let's see, these are derivations. And this is given by the next rule. Following. n minus 1, I equals to 0, minus 1, I, this is a transposition. Following, oh, I think I will need more space, okay. So this double bracket is given by the rule. This transposition, 1, 2, following another double bracket, but this one is written like this. Following a transposition. Because it acts on the tensor product, right? Just to don't forget about it. That's how this acts. So who are these guys? Okay, we just plug in. Huh?
What is n in this formula?
Ah, okay.
Yeah, I think it's just
Yeah. Okay. Yeah. Just take the general case.
0 to 1. So
Yeah, 0 to 1. This is the second derivation, acting on A2, and we take the first component of the tensor product and multiply it by the second derivation, acting on on A1, and we take the second component. Tensor product with this.
So let me
Okay.
make clear a few things. First of all, when we speak about derivations from A to an AB module by module, you need to specify the bimodal structure on the right. So here I believe the bimodal structure on the right is induced by the outer multiplications, right?
Yeah, maybe I will just.
Yeah, again, if erase B, it doesn't matter much. But,
Yeah.
but what is important is that on the right, you need the outer bimodal structure on the tensor square, right?
Yeah.
Second, when you have a map Q from A to A tensor A, whether it is derivation or not, you can always decompose it in sum of tensor of elementary tensors, left and right tensors.
Yeah, this left and
Delta
right.
one, delta two are maps from A to the left leg of the tensor square and the right leg of the tensor square, respectively. And also this the n minus 1, which appeared before A, is I think just reminiscence of homogeneous construction due to Van Den Bergh, where he associates multiple brackets with
Like
multiple
n brackets.
tensors.
Mhm.
Yeah, to similar maps from A to tensor powers of higher dimensions, high tensor powers.
There are triple and quadruple Poisson brackets.
Yeah.
Yeah, that should be fine. But
You know, there
what
is-
they mean and how many there are and what they induce, I think it's an open question.
You know, there is a number bracket.
Sorry?
You know what is number
Yeah,
bracket?
no.
It looks also has
Yeah, it's
special
about it, but
meaning.
probably I would rather say that number brackets might be used on representation spaces from double and from triple brackets, maybe, or from quadruple brackets, I don't know.
Yeah, actually, that's I
That's
erased
a good
erased it.
question.
But this double Poisson bracket with this L, it's also modeled there with three brackets and all this. So we have this map that is well defined, and if A is smooth, then mu is an isomorphism. What is to be smooth? So if our algebra is finitely generated, and omega of this algebra that is defined as the kernel of the map of the multiplication map is projective. Projective in the sense that we consider the A by modulo. Yeah, this means that it is smooth.
Yeah, I believe that you need to mention what is decay of A.
Decay?
I think it's you need to take D2.
Ah.
Not general A.
Yeah, in
Otherwise,
this case
I
it.
don't understand what you have delta 1, delta 2.
I think I can just leave it like this because we consider just
Yeah, but
this case, no?
But you have delta 1 and delta 2. What is delta 1 and delta 2 in this case?
These are just derivations.
Derivation, but from where to where?
Yeah, some of these from A to.
So as I said, you need to double derivation.
Yeah, just to add here too, no?
Yeah, that's the D2.
Okay.
So you take it to the square of derivations.
So I put it. Okay, I'll put it. Okay, indentation should be just out. Yeah, here. Okay. So actually, if we consider A to be the algebra of matrices, we can prove that actually it's a smooth algebra, and we can apply the previous proposition to this algebra. And
So what do you call smooth? You didn't give a definition of smooth.
yeah, just give it like A, it's finitely generated, and the kernel of the multiplication is a projective A by module. We proved it, and we can conclude that actually all double Poisson brackets. Okay, here.
So the claim, I think this is, yeah.
So.
So this is Van Den Bergh's actually.
Mhm. So actually, this one is smooth, and in consequence, as consequence, then all double Poisson brackets are inner structures, means inner derivations. It means actually we can write it, how they look like. So, an inner derivation in this case, if we consider x and y are in the, okay, I will write here, x, y, a and b in the algebra. So
I believe you also need to assume that delta, this element, if you verify a certain variant of don't just take arbitrary element. If you want to get double Poisson, you take a bivector of the sort, but that verifies certain relation. I think.
Yeah, you're right. This it's about this Q, not this one. It's this one. Yeah, just skip it. Okay, let me write what you mean. No, wait. No, actually, it's everything.
No, there should be some double Schouten bracket for Q. Q squared should be equal to 0.
For this one or this one?
For Q.
Ah, for this Q. It's because there are different Qs.
No, that's the same Q, but you just define different brackets using the same Q.
So you mean Q squared equals to 0?
Something like that. Q commuted with Q. There is, as far as I can, as much as I can remember, Van Den Bergh's theorem, Van Den Bergh's paper, he actually uses kind of Schouten brackets on the space of multi-derivations.
No, actually no.
Take category.
Just
But this is just well-defined linear map and linear brackets. But you need also double Poisson bracket condition. Not every n brackets verify double Poisson, the double Jacobi.
no, but in this case we need this mode.
Sorry?
Remember? Yeah, you're right.
Yeah. If you want to get double Poisson, you need to introduce some condition, as far as I can remember. Here it is. Here it is. Map 10. Race map. So this is actually the this is the double Poisson condition. This is the, you see? Yes.
Yeah, you're right.
Yes. Actually, there is some. The construction is a bit more complicated. On the space of these multi-brackets, double multi-brackets, when the book introduces an analog of Schouten-Nijenhuis operation, and then he shows that under certain condition, which looks like this, it's not just this, it's 0 modulo certain submodule. Module subspace. Then what you get in this way will be double Poisson.
What is the motivation for this structure?
It is just to imitate the classical theory. In classical theory, when you work on Poisson on manifold, and you introduce Poisson structures in manifold, then you know that Poisson structures are in one-to-one correspondence with bivectors that verify this condition.
Actually, in
And
this,
you have the same thing here.
in the example of the free algebras that I mentioned, there they modeled some integrable systems using the language of double Poisson brackets. So because Sokolov before they made a relation of integrable systems with algebras, so you can actually model
I've seen
integrable systems with
the
algebras.
Okay, there is a paper by Sokolov and Tov, I believe,
Yeah.
where they study
Hernandez, yeah.
bi-Hamiltonian structures,
Aha.
which are, and bi-Hamiltonian structures are.
And they, right there, they do this relation between algebras and integrable systems. So, yeah, okay. Inner derivations, how they look like, depending on A and B. I think it's just a commutation, yeah. It's It's a little bit long. Just consider the commutation with x, but considering the multiplication as the inner bimodule. And there should, okay, maybe here the whole thing because it's kind of long. So A tensor B minus B tensor A multiply x with the inner bimodule structure, and then we multiply y by the out bimodule structure. In that way, this will be our double bracket. Yeah, just taking an element of the algebra. Yeah, I think that's mostly all I want to show. There are, after this, you can also follow that all semi-simple algebras, their double Poisson brackets are inner derivations. So the next step is to study non-semi-simple algebras already. We are working on it. We take an example of triangular matrices, and we calculated the double Poisson brackets in this algebra. Yeah, so that's mostly all. Some questions?
Example.
Yeah, okay. Because
Okay, that's, well, first of all, when we speak about double Poisson brackets on matrix algebras, first of all, you need to prove that matrix algebras are smooth in this sense. And that takes some, not very hard, but it actually takes some technique to prove. And then we see that all double Poisson brackets are actually, on matrix algebras, are actually inner, in the sense that they are all given by this kind of, by this kind of formula. And the reason for this is that on smooth algebras, smooth algebras, under the condition we have here,
yeah, the projective.
There exists only inner bivectors of this sort, and that's also, I think, it follows from the consideration of
With equivalence.
of the condition on the derivations.
And for
Because all derivations of this sort, the only derivation you have from matrix algebra to any other module of this algebra is of inner condition.
I want to again ask about motivation. What is motivation except for what was the original motivation? Because I know this structure was invited in 2007, 2008.
Actually, the motivation is to find some non-trivial Poisson structures on representation spaces, if they are, and also to relate Poisson structures and the Hamiltonian systems on these spaces to some algebraic structures on A. I think that was the original motivation by Van Den Bergh himself. But the problem is that all examples which exist so far, they are all infinite dimensional algebras. So we just try to fill this gap. Just because in finite dimensional case, it is easier sometimes to describe representation spaces. In infinite dimensional case, unless you work with a very simple algebra, you don't have any idea about how representation space looks like. In finite dimensional case, you can actually try to get something. Not much.
Assumptions. Bolshansky once said that it solves some problem of commutative geometry.
Yes, but that's just the beginning of investigation. You can also try to go further with geometry. But first we need to get some examples.
Yeah.
You see, I was once told about, I think it was someone told me about some very renowned and well-established mathematical school, scientific school somewhere. I think it was somewhere in Odessa, where there were a whole lineage of people doing some research in differential geometry, putting some properties of various quasi-pseudo-Sassakian manifolds and so on and so forth, and speaking some properties of the geodesic flows and so on. But then there's some guy who knew how to solve differential equations. A guy from Vinogradov school, so he knew all these criteria for the existence of non-trivial solutions, which is due to Vinogradov and this how we call this geotheoretic approach. So when he was very idle, sitting at some scientific council, he decided to check if the conditions they need actually allow some example. And very quickly he proved that no such things exist. So the whole business of this group was undermined. So we need to see some examples. Just
Yeah.
to go
Okay. Let's show a non-semi-simple example. So, okay, a non-semi-simple example. Let's consider A as the algebra of matrices, okay, of matrices 2 by 2, of triangular, upper triangular matrices 2 by 2. It's a very simple example and actually not easy to computate, but at least you only have, it can be modeled. Just consider the identity. Let's say the element E0, the element E1, the element E2 with the following relations. Okay, the relations are okay. Okay, follow the notation. So E1 plus E2 is equals to the identity. E1 is idempotent, and same for E2. And also E1 is 0. When we multiply by the left side to E0 and by the right side to E0 by E2, we just get E0. And the last one, if actually we just change the order, 0, E1, and E2, E0, it gives us 0. So these are the rules to follow the algebra of upper triangular matrices. And we want to compute a double Poisson bracket on this algebra. So, what we have to calculate? So, let's say we can see double Poisson bracket here. This was a little bit long, so Not sure what to include. Okay, just for the computations, actually, we can just eliminate E2. For example, we can consider E2 just equal to 1 minus E1. And then we do all the computations considering this. And we just do the computations considering 1, E0, and E1. So the basis in the algebra, the tensor product of this algebra, it's a little bit long, but we just consider this. E0, E1, 1, E0. E0 with E0. And E1, E1, 1, and E1, E1. I think this is the whole base. Ah, no, I forgot. E0, E1. And E1, E0. So actually, what we have to do to compute a double Poisson bracket? Well, every time we have to assign, well, first, with 1, we have already, this is 0. So, and actually, any double Poisson bracket with 1 will be 0. So we already eliminate some options. But for the rest, for example, just E0, E0, we have to determine all the coefficients in this base for the rule of antisymmetricity, Leibniz rule, and Jacob identity. And well, yeah, we did it just by hand, calculating all the possible coefficients. And we got to the result that the form of the possible Poisson brackets are the next. It's just a field. So actually, in the rest of the combinations, they are just 0. This is the only one that it's not 0. So if we want this algebra to have a double Poisson structure, it has to be of this form. And then we can compute the representation spaces and check what are the induced Poisson brackets in these spaces. Should I continue with that? Or?
I think yes. Don't know if you want. Actually, in this case, you can give a description of the representation space and look at the Poisson structure induced from this construction.
Okay.
And this will not be 0. And that means that this structure is not internal. And that's a little bit strange because for every noncommutative algebra, you can think of internal structure in this way, right? But for some reason, there is no such internal structure, no real internal structure for this algebra.
Okay.
Why it is not internal is because for internal structures, one can show that for internal structures, all the double Poisson bracket used by internal structure is equal to 0. So not double, the usual Poisson structure is from inner double Poisson structure. The usual Poisson structure on representation space induced from internal double Poisson structure is 0. So since this double Poisson structure doesn't induce a 0 Poisson structure, it is non-internal. Why? I don't know.
Okay, just an example to see
Unless
how.
they have miscalculated something, but we don't
Yeah,
twice.
could be.
Yeah.
So, the representation spaces, let's say in dimension 2.
This is the original result. This is the original result.
It's rather Abner's result because he was calculating. I was just saying to him what to do.
Have you already published this?
We're in the process, so something
Yeah.
to say.
So, representation space of dimension 2. Just after some process, kind of not that long, but a little bit. Okay.
So it's four-dimensional. You see, this algebra has 4 generators. So we need to choose 4 2x2 matrices. But one of them is fixed, it's just unit, for sure. But the other 3 are more or less free. We have more or less free to choose the other 3. And then we need to modify the choices a little bit so as to choose nice. First of all, to make sure that all these relations hold on one hand, on the other hand, so as to see, just find nice coordinate system. So you can just write down the result, how this is working.
Okay.
Because all these computations, they're pretty tedious.
Just want to also describe how it looks the representation space, just for the record. So for dimension 2, we just consider 1 next 2, 1 over 2, and set. I mean, this is not how you start to approach to calculate the representation space, but after already some process, you can identify the representation space with a manifold, and well, actually with a fine variety. So it has to satisfy x1 over 1 plus x2 y2. These 3 equations. Yeah, and if you look at them, it means like your x has to be in a circle. Some of them they have to be tangent. For example,
Y is tangent to the circle at point x.
Yeah, it's in a tangent line, I think. Yeah, it's in a tangent line. Z, it's in a tangent line to x, and y is just orthogonal, but through the center. It's, for example, the representation space of A2 can be thought as a circle when you have to consider these 3 points and they have to satisfy this equation. So, for example, in the circle, if you choose x here, for example, there's a map in the representation that it's represented by these points. So you consider the line, this line, and z has to be in this line. This is x. And y has to be in this line. Yeah, so the 3 points, they represent only one point in the representation space. So how looks the induced Poisson structure in this representation space? Well, x can be looked as just these functions of theta, of a parameter theta. Y can be looked as just multiplication by a parameter lambda of the point minus x2, x1. It means just to substitute here, this here. And z, just, it can be represented as x1 minus mu. These parameters are free, mu and lambda. x2 and x2 plus mu x1. So we have to determine the Poisson bracket for these three parameters, for theta, lambda, and mu.
It's three-dimensional, essentially.
So after some computations, we get to the matrix of this Poisson structure. It's 0, 0, 0, 0, 0, minus a lambda square, a lambda square, 0, 0. Where a is also free and lambda is free too.
No, lambda is the parameter.
Ah, yeah, lambda is here. And a it's free.
You see, it is pretty strange. It's really simple. It's relative, right? It's at most two. It has a followed by degenerate sign.
And if we follow for the example of dimension 3, actually the representation space of dimension the representation space of n equals to 3, it's kind of similar to this example, but you grow the dimension of each element there. So representation A3, this can be represented as same, let's say x equals to x1, x2, x3, y1, y2, y3, and z, z1, z2, z3, and they have to satisfy also three equations.
Very similar to this.
Yeah, as you can see, x has to be in a sphere, z has to be in a plane that is tangent to x in the sphere, and y has to be in a plane also, but it's parallel to the plane where is z, right? And that only represents one element in the representation space. I also want just to mention that this is a relation, it's bijective relation. Like one point here that satisfies these relations is one element in the representation space. So the induced, okay, x can be considered to be just.
It's a point in the sphere, right?
So
So
it has spherical coordinates, so x depends on two parameters, theta and phi. Yeah. Z Y and Z.
There are two parameters for y because
Yeah.
y is perpendicular to x, and hence it's dimensional space.
Lambda mu. And Z. This depends on. Just want to check if it's also depends on the same ones. It's just I'm not that sure. No, it depends on different ones.
Which you don't remember.
Yeah, I'm trying.
Describe C.
Mhm.
And I remember there were two parameters. Okay.
Okay, yeah,
I just
let's
don't
say.
remember.
Yeah, now I found it. Alpha, beta, and let's say this one depends on delta and gamma. So this is 6-dimensional. We have to determine the Poisson bracket for these 6 parameters. And the relations are alpha with gamma is equal to lambda alpha squared, alpha with delta is equal to lambda alpha beta, beta gamma, lambda alpha beta, and beta delta is lambda beta squared. So this gives us the matrix. Well, this is kind of big zeros.
It's 6 by 6 matrix, right?
Yeah, but okay. Actually, most of them are 0. So I will just write this part, and the rest are whole 0.
Yeah, there will be this 2 by 2 part,
Mhm.
which is non-zero and it's symmetric. And this is symmetric.
There is just 0 here. And here's another, well, just the same, but with different sign.
And alpha squared as well.
Yeah, you're right. Mhm. The rest are just 0.
Again, pretty funny pattern as you see. It is singular. It has different ranks and different points. And
But they are the same rank as the previous one, no? Both
no,
are.
it's not always the same, actually. Sometimes it has rank 2, sometimes it has rank 1. Oh, no, sorry. It always has rank 1. Sorry, you're right. It always has rank 1. Because these two lines are always linear independent. So it always has rank 2, just like previous, but pretty funny way.
Yeah, and the rest of representation spaces was already kind of more complicated. So yeah, I think these are good examples already.
So again, it means since these representations, since this Poisson brackets are non-zero, it means that the structure we described is not given by a commutator with some element. Because otherwise it would give you trivial bracket, just identically 0. What happens? Where are all internal structures? That's not clear. Maybe it's not hard to answer probably, but we didn't try it.
Okay, yeah, that's all right now.
Thank you. Okay, are there
Okay.
any questions from the audience online?
Did you try to find any connection with the Poisson structure or the non-commutative case that we set up with Paul Van Hacking? For instance, you can try
It's possible. They haven't. It really takes some time.
Poisson algebra.
I feel like it would just get 0 for the double
There
Poisson.
was some further remark by Alexander. Please continue, Alexander.
I just want to understand if there is any relation between the double Poisson algebra approach and what we did with.
Actually, double Poisson approach is not the only one which exists. There was recently another generalization of this approach due to Semyon Artamonov, who suggested to consider not just, actually by definition, in his case, double Poisson brackets, well, just generalized double Poisson brackets are anything which induces Poisson brackets when you pass to universal trace space, I believe. We call it like this. But you can also, actually there are lots of approaches. It also, this Artamonov's construction also uses Poisson structures on representation spaces. So I think that the ultimate purpose of all these constructions is to say something about Poisson structures on representation spaces on classical level, and derive some certain consequences from this in terms of Hamiltonian equations, Hamiltonian systems on representation spaces. Whether you can solve in a universal way, in a general way, all such equations for all representation spaces, or probably you need some specific approach to every representation space, well, separately. It's quite a big question, quite a good question, in fact.
Now, there are two things. One is find Hamiltonian equations and have actually Lie structure, not Poisson. Poisson assumes Leibniz rule.
Yeah.
And that is why you have Poisson algebra. For Lie algebra, you know, this structure, like you have traces, that what we did long time with Volodya Sokolov in 2000, I think. But it's not a Poisson algebra.
Yeah.
Because there is no multiplication if you have these traces.
Sure.
Traces, no way, no reason to multiply. Now I just want to see that is any relation between different approaches.
Well, we have just started to study this. We tried to compare this approach with Artamonov's approach, and actually didn't receive anything new in that case. Maybe your approach will yield something different. I haven't yet tried this.
Because I checked some articles of Sokolov about this trace.
Yeah, we can. Sure.
Yeah, because actually the Poisson bracket, there are some details of how it induces the Poisson bracket. So it's actually a Lie bracket, but
Yeah, first
you have to
Lie
modify a
bracket,
little
to
bit.
check the Leibniz rule. It's different. Okay. Any other questions? Okay. Then let us thank the speaker and see you next time. Probably next time. I hope that Ilya will be able to make a talk next time, and it will be online, definitely, because we are going to to leave for a conference, me and Hernandez. So next time we'll meet online, and I hope that Sashka and Ilya will be able to talk to us.
Thank you.
Thank you.
Yeah. Let me wash my hands. Come.
Конференция будет.
Oh, can you help me with this? With the microphone?
Oh, yeah, sure.
I don't want to.
Yeah.
Sorry?
The people,
Jun Hugo.
he asks about you. He asks you something. Can you ask again?
Me or Alexander Boris?